Hi, welcome everyone to the Builders User Group for App Developers. For today's session, we have Getting Started with Apache Iceberg. Our speaker is Ryan Blue. For today's agenda, we're going to be able to have a few welcome and introductions, and then Ryan is going to talk about Iceberg tables. He'll give us an overview, and then we'll leave some time at the end for attendee questions and answers, and we'll have just a few closing remarks as well. So thank you all for coming to this user group. We love to have these user groups that are virtual, where we can discuss best practices, where you can grow your professional network, and then of course stay current with the things that are happening today with Snowflake. If you have not yet had an opportunity to join this user group, we'd love for you to go to usergroups.snowflake.com/app developers. That's the homepage for this developers user group. All you need to do is click join us and you're in. You'll be receiving updates about future sessions as well. For those of you who also enjoy meeting in person, there are quite a few local chapters. You can explore by the region and find one close to you. All right, so with that, we'll go ahead and introduce our speaker for Getting Started with Apache Iceberg. Ryan, as most of you know, is the co-creator of the Apache Iceberg. He's also a member of the Apache Software Foundation. He's previously worked for Netflix, Cloudera, and the US government. Currently, he's the co-founder and CEO of Tabular, which is a central table store for all your analytic data that can be used anywhere. And so with that, I'm going to turn it over to Ryan. Thank you.
All right. Thank you, Joyce. Let me put my slides up really quick. All right, everyone can see that? Great. So it's great to be here. Really happy to, always talk to user groups, and hopefully we'll have some really great questions and discussions at the end. What I'm going to cover today is just basics about Iceberg. I know that Iceberg's been coming up a lot in both materials from Snowflake, as well as just general blogs and media in the data engineering space. And so this is just a really quick introduction to where did Iceberg come from? What does it do? What is the purpose of the project? And then sort of like how we use it and what it unlocks. So let's get started. The first thing I want to talk through is why we created Iceberg in the first place. So what we wanted to do was actually fix a whole bunch of problems on the data lake side of data infrastructure. So Netflix had essentially a really, really large data lake that was built using technologies outside of Snowflake as well as Snowflake. So we were using essentially the Hadoop ecosystem of projects with Trino, Spark, Snowflake, Hive tables, Parquet files, just a lot of different things. And what we found was we had a really like 3 categories of problems that were causing just a lot of problems for our data engineers. So the first was just correctness. In the older table formats and the sort of Hive lineage of formats, which is where you just keep all your data in S3 or HDFS or some underlying format, they were too simple. They just kept files in directories and listed things, and what you ended up was you had correctness issues because you can't make atomic changes or have transactions on top of just files in a file system. You need something more sophisticated, something smarter. And so correctness issues plagued our developers and our data engineers. Basically the simplest example here is, how do you overwrite part of your table if you have to make files disappear and appear atomically? It's just not possible. Correctness problems are really concerning because you either delete the data first, or you duplicate the data and then go clean it up. And both of those have their challenges, especially for downstream answers. essentially your queries can lie to you. The next thing we were dealing with was cost and performance. So how do we actually get these things to scale now that we're working with S3? How do we get data faster and eliminate more data from what our processing engines need to read? That was a big problem, but not really one that I think many people care about. Things just get faster in the iceberg land. And the third set of problems that we were dealing with were just data engineering productivity problems. And this was largely because we didn't have a table format that actually gave us a proper abstraction over our data. What you had to do was care very deeply about the size of files inside your tables and things like that. You couldn't make certain changes to table schemas without corrupting data and things like that. And it was just a very hard space to work in. And what we realized was that all three of these areas overlapped in the table format. They had the same source. Like the problem was just one thing, was that the way we were keeping track of data and saying these data files make up a table was just wrong. It was not performant, it was not correct, and it caused all of these productivity issues. So we created Iceberg to solve that problem. And we basically stole a whole bunch of ideas from the data warehouse and database space to take our data lake and make it function like a data warehouse. So what is Iceberg? Iceberg is an open standard for keeping track of what is a table, and we're targeting specifically SQL behavior. Now, I added something here. So why is an open standard a goal? Why is this something that is important? Well, when we created Iceberg, we basically had to build this new way of keeping track of data, of saying these data files make a table and this is a version and this is how schema evolution happens. We had to take all of those concepts and that library, and we built it into Trino. We built it into Spark, we built it into Pig, we built it into Hive, and all of these projects. And we said, that was a ton of work. We don't ever want to have to do that again. So we made it open source, and we tried to make this a standard that other companies and other projects can invest in, because we all want to be able to access the same data at the same time. And so what the importance of an open standard is really gaining this commercial investment. It's building something that other companies and especially other vendors can build on top of. I think that there are two aspects of this that Iceberg really focused on and did well. Number one is a strong technical foundation, and we'll talk more about that in later slides with capabilities and things like that. But essentially, the consensus is Iceberg is a strong enough technical foundation that we can build on top of it. The other is this open standard and sort of open community. We need a neutral community so that both AWS and Google can, confidently invest time in adding support for Iceberg tables, for this format, so that you can truly use this data anywhere. Snowflake and Starburst, or Dremio and Cloudera, we all need to share the same data and have some common understanding of what it means for files to make up a table. And if you have, one company that, say Cloudera had their own special format and they gave themselves special features in that format, the other players here wouldn't invest. So it has to be a neutral and good community that everyone can invest in. So it is really, really important that we have a standard and something that is neutral here. So the other half, why do we care about SQL behavior? And this might not be obvious, because coming from Snowflake and the data warehouse space, this is just how tables have always acted. So I want to poke a few holes in the data lake space as it was before Iceberg came along. And really what we did was nothing special. It was just asking the question, hey, what if we applied the database fundamentals that are baked into many of the other engines out there, right? These are the things that Postgres and MySQL do by default. Same thing with Redshift or Snowflake. This is just updating the data lake space to use these techniques. So the first one is fixing schema evolution. Now, what we want with schema evolution is for it to be instantaneous, right? You don't want to wait for your add column to go and rewrite 10,000 data files or 1,000,000 data files, right? We don't want it to, if you're dropping a column or renaming something, you shouldn't have to go and rewrite all of the data because that's extremely expensive. So it needs to be a metadata operation. That's, I think, pretty obvious, but in the Hadoop space or the data lake space, we also had issues with just things that I like to refer to as undead or zombie columns. So if you were to rename a column or drop a column and add it back, you could easily get in a situation where data that you thought had dropped or was no longer accessible comes back to haunt you. And that was a really big problem. This is something that you don't expect. If you drop a column and add one with the same name, it's a new column according to the way databases have worked for the last 40 years. So what we ended up with, and this is on along the lines of what I talked about earlier, all the problems for data engineers, was just this introduced days of headache. People would drop a column, add it back, write data in a downstream table, and then come back and say, why is this all corrupt? And now it's leaked downstream and possibly downstream of that, and you have to go clean things up. So we wanted schema evolution to just work like a database should. And so we fixed that. The other big departure in the data lake space was partitioning, where partitioning is a really important concept for breaking up your data so that you can find the pieces of data that you need for any particular task or query. But partitioning in Hive and Hive-like formats, including Hoodie and Delta, has a lot of challenges because you actually supply the partition values yourself. So basically you're saying, okay, I'm going to break my data set up into days, and I'm going to only read the days that I need to satisfy a query. Well, if you are supplying that date yourself, then you have all of these hidden bugs and correctness problems. Like, well, where did you get that date? Did you get it from event time, or did you get it from processing time? Did you use the right timestamp, or sorry, time zone to convert it into a date? All of those things need to be thought through by the data engineer writing data every single time you write. And that was a huge problem. And this is still a huge problem for a lot of formats in the data lake space. So what we did was we just kept track of the relationships between a column and the way you want your table laid out or structured. And it got rid of all of those problems. So now if you filter on a date, if you filter on a timestamp, we can automatically detect, oh, hey, we're laying out the data according to that structure, and we can really quickly and easily find the data that you need without making mistakes or without allowing the users to introduce mistakes. And this seems, I'm sure, extremely simple. Why would you not do this, right? Why would you have something that the person querying a table needs to think about every single time, in addition to their work and how they are preparing data and what they're doing with it? And you're right, it makes no sense. And this is really why we wanted to restore the SQL table abstraction. Tables should just work like tables, even if you're in a data lake. And so we sort of have this mantra in Iceberg that Iceberg should be invisible. People day to day should not think about Iceberg at all. It should just function like a table, and you should never really see it. So we want to do that in two ways. We avoid unpleasant surprises. Zombie data columns are definitely an unpleasant surprise that causes you a lot of headache. We also try not to steal attention. So we don't want to have concepts or things underneath the table layer that people need to care about deeply. The best example of this is, how many data files did you write out? And is that going to cause inefficiency when you read the table downstream? We really don't want people to care about that anymore. We want a way for services to come and rewrite that data. Or we want the data to be written the right way in the first place without requiring a person or a DBA to make sure that's happening. So that's the goal of Iceberg in general, is to provide this abstraction underneath which you don't need to pay attention. So that's like step one. At this point, these are table stakes. This is what databases do. And now we have a data lake format that acts like a database, which is really, really cool, especially if you're from the data lake world. Now, there are other benefits of Iceberg that I think are more interesting and better to pay attention to. So what are the advantages of Iceberg? Well, so the first one is Iceberg supports engines that build expressive SQL. So these are declarative row level or row focused commands that allow you to do very fine-grained updates or changes to a table, while still letting engines optimize and do the right thing with those commands. So engines, if you were doing these things by hand, you might have a pattern that is like, read all the data for a day. Take the new data for that day and join it together, figure out the updates to rows and things like that, and then overwrite that original day's worth of data. Now, that's really expensive because you're reading the entire day, you're overwriting the entire day, and you may only update a row or two, if that. So what merge allows us to do is to use techniques like dynamic pruning or storage partition joins, or all sorts of other things that are supported by the table format itself that you don't have to care about. You just go and say, you know what, when there's a change, update the corresponding row like this. If there's a corresponding row, increase this count. And if there's not a corresponding row, insert it, something like that. And that's what we're showing here on the right. That allows the engine to go and find, oh, hey, we only need to read one data file because only one data file is being updated. And Iceberg also supports things like, rather than rewriting this entire data file, we can just say, hey, that one row that we're updating, that's deleted, and it's replaced by this other thing. So the format itself allows us to do much more optimized and much faster updates and queries, while still giving people a lot better interaction with their tables, because it's so much easier to read and understand a query like this or a command like this than a command that is like, hey, read a whole bunch of data, join it with this, drop some rows, and then write it back. All right. In addition, we get some very nice properties out of Iceberg and just the way that Iceberg stores data. So every change in Iceberg actually produces a new metadata tree. And this is because we are managing a collection of files as a SQL table. We don't update the entire collection, and we're using immutable files in S3 because you can't just go and make random access changes when you're using an object store. And so the way we had to construct Iceberg gives us a very nice property that we continuously make small changes to this metadata tree and this file tree that you never have to worry about, but each change produces a new root. And by keeping track of all of those tree roots, very much like Git, if you're familiar with that, you get a history of each version of the table going backwards in time. And that's a really cool thing, because every change produces a new snapshot. And you can read any of those snapshots that are still valid as time travel. You can also roll the current state of the table backwards to another point, and say like, oh, hey, let's roll that table back to before we started receiving bad data from downstream, or sorry, upstream. So because every change is a snapshot, we have this, great history for debugging and going backwards in time, consuming the table incrementally as a stream of updates and changes, or rolling back to healthy states. So, we can time travel very easily, as we see here. You just add for timestamp as of some time, and you'll go back to the table state as it was at that time. The other really cool thing is, if you don't want to keep, if you want history that's longer than the default window of changes that we keep around, you can actually go and name some snapshots and say, okay, keep this for 2 years. Create a tag that was Q1 2023. Those are the financial tables that we're auditing, and we want to retain those for audit purposes for 2 years. And you can retain the exact copy of data, and it's that easy. Last example here is just how simple it is to roll back to a particular point in time in a given table. So Iceberg's metadata model unlocks some pretty cool features. We also, sort of along those same lines, we have new engineering patterns that are unlocked by the same thing. So not only can we tag older versions and keep multiple versions of a table around for some period of time, we can also branch and keep track of multiple different histories in the same table that are based on some, common version in the past. And this is not actually a transactional thing. Branching is actually just for testing and validation. So you can make changes and write into a table and then check those changes and make sure, hey, we don't have any nulls in this column, right? Before you go and publish that result. The power of that is that you're keeping changes from moving downstream. So if you have a problem with your data, say you receive bad data from upstream, it fails those audits, and then you don't release it. And so you don't have to go clean up and reverse changes to 10 different downstream tables. You catch it where it happens and stop processing immediately. Then a person can go and take a look, see what the problem was, fix it, and get that table back into a good state. And then downstream processing can pick up from there. So this is a great technique for integrating audits into workflows, as well as testing new code. So you can create a branch that is for your new way of updating this table. So I'm sure there are a lot of DBT users out there. What if you could not just create a table like the one that you intend to update and work with that? What if you could actually base the test branch on the table state itself and make essentially a zero copy? That allows you to test things like merge, where the update is not just based on the incoming data, it's based on the current table state as well. So Iceberg allows a lot better engineering patterns that are lighter weight because all of the table data is in a single place. Iceberg also supports arbitrary single table transactions, which is kind of nice. As I said, because we're operating on a metadata tree and sort of keeping track of which snapshot is correct, we're pointing to the correct snapshot. You can jump snapshots, and that gets you single table transactions. We're also working on a way to coordinate this and get multi-table transactions working as well. The next beneficial pattern or reason to use Iceberg is a little, I don't think it's as obvious as the others, but it's one that I really think is important. And it's declarative data engineering. For a really long time, data engineering, at least in the data lake space, and I think to a certain extent in data warehouses, has not been truly SQL-like. So, SQL is a language where you declare what you want, and the database is responsible for figuring out an optimal or an efficient way for getting you that data and doing those operations. Data engineering has been very focused on sort of tricking engines, tricking Spark or tricking Trino into doing the right thing. So we have like hints that say, use this parallelism at this point in the write, or you have to specify an ordering when you're querying, so that when you write that into a table, you have clustered the data in the table. That's really weird, because that puts all this onus on the person writing and the person thinking about a pipeline, who should be thinking about, how am I getting the data cleaned and correct and available? They shouldn't be thinking about this other dimension of, how do I tune it at the time that I'm writing the data, if that's even possible. So instead, what we want to do is follow this SQL-like pattern, where you tell the database what you want in terms of how to partition your data, how to cluster your data, even things like tuning settings. How should I structure data in my Parquet files? And then let the infrastructure get you there. So in this case, what we want to do is create a table, this accounts table, and say, oh, it's partitioned like this. This is how I want the files and the data laid out and separated into chunks. I also want it distributed at write time by the partition and locally ordered within each task. And you do that just once, right? You say, this is the ideal state of this table. And then the engines are responsible for reading that from the table and getting you there automatically. So the write in this case should just be insert into accounts, select account ID and balance from my data, right? So it should be very, very easy. And the configuration of the table tells the engine exactly what to do, rather than saying, oh, and order the things and distribute them and use this number of tasks and so on. We want to push more and more to the infrastructure itself. This does two big things. So declaring what you want is the best way to manage multiple engines, which is one of the big things that Iceberg unlocks. It's very easy to use a streaming system like Flink, a query system like Snowflake, and Spark for ML, and have all of those engines do the right thing with your table. So you don't want to configure each engine individually. That would be a massive headache, and something that Iceberg is trying to help you avoid. The second big thing that this does is it unlocks automatic optimization. So in cases where you don't really want to go and set the Parquet dictionary size yourself, I've literally only seen people care about that once or twice in my career. It's just not something that data engineers have the time for. But centralizing these configurations at the table level gives us an ability to go and inspect that table, look at what we know about how it's being read, and automatically have a place for recommendations to go. So we can automatically optimize that table and then have those changes take effect when the scheduled Spark job or scheduled Trino job or Flink write to that table. So this is actually a really powerful pattern that I really hope people think about more. And unfortunately, I think that we're going to be time constrained. So there are a ton of other things that I think Iceberg does really well that are super cool, but we're not going to dive into too much. So, in terms of performance, I said this was one of the things that we had as a goal, cloud native tables using S3 that are, highly performant. Well, Iceberg brings in a lot of features to make that happen. Better column level filtering during job planning, automatic pruning. We actually index both data and metadata. so that you can find the data that you want very, very quickly without needing to parallelize or cache or do things like that. Iceberg is also portable. We made this so that it can be re-implemented in other languages. So I think we have a Rust implementation coming, and we have an implementation in Python that can be used today to pull data into, say, DuckDB or Arrow. There are no JVM or Spark specific features, and that is one thing that makes Iceberg really unique in this area. Hoodie is pretty much completely tied to the JVM, and Databricks' Delta product has features that are extremely dependent on parts of Spark. So the fact that Iceberg is portable and can be used anywhere is really special, because you want to be able to use it with multiple engines. We also have multiple update strategies. I alluded to this earlier when I talked about merge. We can rewrite everything eagerly, or we can use deltas and sort of defer work to read time, or we can write the deltas and then use a background service to merge that into data files to sort of have this balance of very quick writes, work in the background, and reads that are performance optimized. Then there's also layout evolution. Iceberg is quite a bit more than I can cover in a 30 or 45-minute session. So there's quite a bit there, and I'd encourage you guys to come and join the Iceberg community and check out all the other stuff that we can do. Now I just got very deep into features, and so let's pop up the stack a bit and think about why. We've got a lot of reasons for the way Iceberg was built. We know that we want SQL behavior everywhere. We want a format that multiple engines can invest in and deliver, as a common data layer. We also know that we've got a lot of good features. We want people using declarative approaches. We want those approaches to include high-level commands like merge, things like that. We also want the performance and optimization that Iceberg gives us. So what are we really doing though? What is the goal or the overall aim? So what does Iceberg unlock, and why should we use it just at a very high level? So I think Iceberg unlocks really cloud native data architecture. And I think this is cloud native in a somewhat new way, because we are not just, designing the format itself to work really nicely with S3 and cloud object stores, and to, sort of do a better job with fewer round trips to a cloud service. It's not just that. What does cloud native data architecture actually look like? At Netflix and a lot of other companies, what we wanted was the behavior of a SQL warehouse, right? We wanted those SQL guarantees. We wanted the high-level plans. We wanted people to be able to rely on the database and the engine to take care of all the low-level details, right? We essentially wanted people to have the productivity of working in a SQL data warehouse with those strong guarantees. Keep Iceberg invisible. Don't let your data layer distract you or cause you trouble. At the same time, we wanted to be able to have truly separate storage and compute. So we wanted this flexible compute that was sort of baked into our assumptions of how the world worked. When we built Iceberg, we had multiple engines. I mentioned Hive, Pig, Trino, Spark, and we were also shipping data off to Snowflake. So we had 5 engines that needed to work with the same data sets. And that was just an assumption that we had to do this and make it safe for you to make changes in Spark without corrupting your queries in Trino or Snowflake. So the world of cloud native data architecture is where your data is your center of gravity, and that is stored in S3 and managed for you without needing to go to a particular engine. Everything should work natively with it, whether it is batch or streaming or ad hoc. whether you want to use Python and Arrow or Pandas to do, local analysis, and you also want, very big jobs doing ML feature training or, feature aggregation in Spark, or, very fast queries from Trino for running a dashboard. We want any language or framework to be able to coexist and operate at the same time on a single data set. That's really what I think of when I think of cloud native data architecture. And that is exactly what Iceberg is unlocking. And that's what basically all of these companies are building. None of the companies that use and contribute to Iceberg are trying to standardize on a particular engine. I think that we all realize that the data space, or the space of data architecture, is far more complex than any one thing is going to than any one framework or language or way of working with data is going to support. We're always going to have ML workloads and warehousing workloads, and while we might not be able to use the exact same tools, or maybe it's just more efficient for a team to use the tool that they're familiar with, we want them to share data. We want them to have this common data layer that that underpins everything, without making a copy over here for this thing, or keeping those two things in sync, because copies and syncing just generate a lot more problems. How do you control access to the copy that you made? How do you make sure that it is up to date? And you might already have these problems where you have 10 copies of a data set. You don't know who made them. You don't know when they were last updated, and things like that. So, this is the architecture that I think all of us are working towards. And I'm really excited about this future. So really quickly, I do have a picture of it, which is great. Essentially what we want is this picture where Iceberg sits on top of S3 or Google Cloud or Azure, and basically defines what your data looks like and how we interact with it. Then it's ready for consumption from any of these engines and any of these frameworks, whether it's Python and DuckDB, or Flink streaming data with exactly one semantics into a table, or Snowflake with their super fast queries, doing data warehousing workloads. I think that we are also missing a couple things, which is what my company does. So you might be wondering, like, what is Tabular? My company basically provides a managed Iceberg service with access controls, background services to keep your data clean, and things like that. We're trying to enable this multi-engine world, or cloud native data architecture. Don't want to talk about Tabular too much because this is about Iceberg, but we're just trying to support the world that Iceberg unlocks. And with that, I think that's about it. I think we have some time for questions and discussion. So let's hopefully, I think you guys can add questions to the chat, and we can talk about it.
All right, so thank you, Ryan. Plenty of time for questions. Let's go ahead and open it up. If you want to put your question in the chat, or you want to ask it directly of Ryan, please feel free. We'll give you a few minutes to come off of mute if you need to. And first question, is Databricks also involved in this initiative? Great question, Ryan.
That is a great question. So I think that Databricks is very much involved in this sort of future state where we have cloud native data architecture. So in many ways, Databricks is one of the engines that you can use, certainly with Iceberg tables. They are, however, not interested in collaborating with others. So, I mentioned earlier that Iceberg is a neutral and sort of standard format that tries to be a place where all vendors can invest and sort of play on equal footing. Databricks has a proprietary format called Delta that does the opposite of that. They've done multiple rounds of releasing new features to the community, which is great, but they tend to hold features back to allow Databricks, to have a performance advantage. Now, the problem with that, I think, is that it puts other vendors at a constant disadvantage, and those vendors are not going to invest in the format and making it the best because Databricks is not allowing them to. So I think that if you want a true version of this data architecture where you can actually use any engine that you want something that's going to work well with all of those engines. And that is, in my opinion, Iceberg. I'm clearly very biased.
Great answer. All right. We'll give it a few more minutes for other questions. So I'll ask a question in the meantime that I've seen asked. And, you mentioned that this is, a great opportunity for the community to get involved. If someone wants to get involved, what would be the next steps for them?
Oh, that's a great question. So we really love when people are interested in Iceberg and want to join the community. There's a community page on iceberg.apache.org. Iceberg's an Apache community. And if you're interested in contributing to the project, I would encourage you to join our mailing lists, join our Slack community, get involved at our, there are ways to get involved on our community page. We love to hear from people. This is about, the project is a really exciting place because we want to make, all of these new architectures possible, right? It's really cool to be able to stream data into Flink, immediately query it in Snowflake, have background services that are running to do certain updates and maintenance tasks and automatically optimize data as it comes in. Like that's the very exciting space of technical things that we're doing. And we love it when people want to come and help.
Awesome. Great. Another question. What features does Iceberg offer that other table formats do not? So in other words, what advantages does it offer?
So, a lot of the things that I talked about today are actually not represented in other formats. So the lowest bar is correctness. This is, I'm sure you've heard of ACID semantics for database, tables and things. That eliminates Hoodie. Hoodie doesn't have ACID semantics, so they don't support concurrent writes in any way. While they say that you can do it, you just might drop data when you're reading it, and things like that. So definitely correctness eliminates Hoodie from the running. They also don't have a lot of the higher level features, the metadata indexing, correct schemas, things like that. So in terms of the two pieces of like why companies are adopting Iceberg, they don't have the technical foundation in order to really play in this space. On the other hand, Delta Lake, I think I pretty much covered their, Databricks does release new features for it every so often, but it's not an open community. It's not really an area where all of the development is happening outside of Databricks. It's really that Databricks holds back a lot of features for themselves. Now, Delta does do a good job in terms of correctness. There are some things like Delta pretty much assumes that Databricks is going to be running your tables and your deployment, and you're going to be using Databricks for streaming. You're going to be using Databricks for ad hoc queries. You're going to be using Databricks for ML workloads. And so a lot of the like tuning and settings and things like that are standardized and centralized in Iceberg are ignored in Delta Lake. Because you only have one engine, why would you need to coordinate across engines? So, some of that declarative data engineering stuff that I was talking about is just not represented over there because they want you to use Databricks. And if you're in this single like vertical engine world, they don't need a lot of the features. They also don't have things like metadata indexing and some of those things. I'll stop.
Yeah, no, great response. Let's see what we'll give the chat just a few more minutes to see what other questions that we have coming up. And
So,
in the meantime, Ryan, for folks that want, to follow you and reach out to you, I know they can reach out through you, through Tabular, but any social media or any place where you would like folks to connect with you directly?
oh, feel free to reach out on LinkedIn. That's primarily what I use. I don't tweet or really do much in terms of social media, unless you count Apache communities.
Oh, there you go. Yeah, perfect.
Yeah, there is a comment here I see that Databricks Delta Lake does support ACID, time travel, schema enforcement, schema evolution. That's true, they do. So a lot of things in Databricks are pretty good. Again, the assumption is that you're using Databricks for everything. We've actually talked to quite a few people who they tried to use the open source Delta and didn't really make it. There are just subtle differences where you really need something managing your deployment, and there appears to only be Databricks there. Databricks also doesn't have hidden partitioning. They have a derived columns table property, but it doesn't work like hidden partitioning because it's only Spark. So when I was talking about assuming that you're in this Databricks world, yeah, the certain features of the table format only work in Spark and Databricks. And that's a huge problem. And one of the reasons why you probably won't see great support for Delta in Snowflake, right? Because Snowflake isn't going to run a Spark cluster just to be able to write your data correctly into your table. And defining what is correct in that case in terms of Spark expressions and Spark concepts, doesn't make any sense. So it's that portability where Delta is tied in certain ways to Spark directly.
All right, great answer. We've got another question. Which of the tools or SDKs support merge statements? For example, I can see that Spark SQL supports merge operations in the Iceberg documentation, but Flink does not. Is this merge functionality limited to certain tools?
So yes and no. Not all tools have integrated Iceberg support. So merge is supported in, say, DuckDB, but it hasn't been implemented for Iceberg tables yet. I'm told that they're working on it. Then there's the category of batch systems versus streaming systems. Now, merge is really a batch concept where you might have to read 90% of a table in order to perform a merge because you have so many records being updated. So it's really a data warehousing concept. And as such, it's supported in the batch systems like Trino, Spark. I believe it's supported in Hive, although I haven't checked that recently. And Dremio and Snowflake and so on, right? Those engines all support it. Flink doesn't support it because it's extremely costly to do merge statements in a streaming fashion. Because you've basically got to say, okay, I have this row coming in. Now I need to find the corresponding row anywhere in the data set. It becomes a point lookup. And that's extremely inefficient at scale. So, what we tend to see is like not doing merge statements in streaming. And that's certainly not where the community is investing its time.
Great, thank you. All right. All right, Ryan, I think we have time for another question. So what are the upcoming plans to read from write to Iceberg tables using Snowflake? Great question.
Yeah, should Snowflake people answer that? Because I'm not the best. I know some things, but I don't know what is public or private or going to be announced shortly at the at Snowflake's conference. So
That
I probably should not answer that question.
that sounds like something you're absolutely right. It sounds like something that we should be looking forward to at the Snowflake Summit. I think there's going to be a lot of really great announcements. So great things coming up specifically from Snowflake. Unless someone on the call from Snowflake wants to take that, we'll table that for the Snowflake Summit, where lots of great information will be released publicly.
I know that there are announcements planned. I can't tell
Yes.
anyone what those are.
Yes. Well, we won't make you break your confidence. So we appreciate that. We want you to keep your confidentiality there. All right. Well, with that, we'll go ahead. Ryan, is there any last comment that you want to make before? Actually, we do have one final question. We'll take this last one. How to get involved with Iceberg? How do we get started, and how do we contribute?
Yeah. So contributing is a matter of joining the community, finding problems that you're interested in, and talking to people on Slack, opening PRs, talking to the dev list. We love contributions. In terms of just getting started, there are quite a few ways to get started. There's a getting started page on the website that takes you through, locally getting something up and running. You can sign up for, say, Tabular, and use a local Spark cluster. We have a local Trino image. You can sync our tables over to Snowflake. Those sorts of things are all possible. We also have integration with Starburst if you want to use a cloud-hosted Trino solution. It's pretty easy to go sign up for Tabular, create a couple tables after connecting Trino and Starburst Galaxy, read them from Snowflake, and that sort of thing.
Fantastic. Sounds like there's lots to do after this this call. For people who are interested, please feel free to reach out to your account rep to request joining the Snowflake private preview. So that's one thing. For those of you who are on the call, definitely, if you have an interest in Apache Iceberg tables, definitely reach out to your account rep to join the Snowflake private preview.